20 billion electron volts, a gamma-ray excess rising from the galactic center in a halo pattern. 15 years of telescope data pointing to the same energy signature. The Fermi Space Telescope did not interpret this, it recorded it. The central question: has the invisible scaffolding of the universe, the substance that outweighs all visible matter 5-1, finally announced itself, or is this the latest false echo in a search approaching its centennial? 5-1, let that settle. Galaxies spin too fast. The outer stars should escape. There is insufficient visible mass to anchor them gravitationally. They do not escape. Something unseen holds them in place. That something comprises 85% of all matter in the cosmos, dark matter. The name misleads. Invisible matter would be precise. It emits no light, reflects none, passes through ordinary atoms without interaction. Its existence is inferred solely through gravity. The way it warps space-time, bends the trajectories of distant photons, prevents galaxies from disintegrating under their own rotation. 92 years since Fritz Zwicky calculated its presence from galaxy cluster velocities in 1933, no instrument has captured a dark matter particle directly. Not one, not anywhere, until, perhaps, November 2025. Professor Tomonori Totani of the University of Tokyo's Department of Astronomy published his findings on November 26 in the Journal of Cosmology and Astroparticle Physics, a single-author paper. In contemporary astrophysics, where collaborations routinely involve hundreds of cross-checking researchers, this is rare. Totani worked alone. The achievement carries weight, so does the vulnerability. His analysis: 15 years of Fermi Gamma-Ray Space Telescope observations, over 5,000 days. The telescope scans the entire sky every 3 hours. The signal Totani identified had been accumulating in that dataset since the mission began, layered beneath cosmic background radiation, unresolved point sources, and instrumental noise. Why did no one find it earlier? That question has an answer, and it matters. The answer to that question, why 15 years of accumulating data went unnoticed, bears directly on whether the signal is real or an artifact of the very methods used to find it. The excess appears at 20 GeV, not a range, not approximately. 20 billion electron volts, matching theoretical predictions for weakly interacting massive particles, WIMPs, a candidate dark matter particle class proposed decades ago. The mathematics: if a WIMP carries a mass of 43 GeV and two collide in mutual annihilation, the resulting gamma rays emerge at roughly 20 GeV. This energy was predicted before Totani's analysis. The data arrived at the prediction, not the reverse. The spatial distribution is equally specific. The excess does not spread uniformly. It concentrates near the galactic core, then fades outward in a profile consistent with dark matter halo simulations. The invisible spheres of dark matter predicted to envelop every galaxy. Correct energy, correct shape, persistent across 15 years. Yet Totani does not declare detection. His paper presents a candidate signal, an anomaly consistent with dark matter annihilation, awaiting independent confirmation. The title reflects this precision. 20 GeV halo-like excess of the galactic diffuse emission and implications for dark matter annihilation. Implications, not conclusions. The distinction is not rhetorical. Dark matter research carries scars. Every prior claim of direct detection, every statistical anomaly, every unexplained excess has resolved into something mundane. Instrumental drift, unmodeled background sources, misidentified pulsars. The signal exists in the data. That is not disputed. What produced it remains the question, and whether the answer, after 92 years, is dark matter annihilating in the halo surrounding our galaxy. Dark matter does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any measurable way, except, perhaps, when it destroys itself. That is the hypothesis at the center of Totani's analysis. Not that dark matter was passively observed, but that it was caught in the act of self-annihilation, converting its own mass into a burst of gamma radiation at a very specific energy. Understanding why that energy matters requires a brief descent into particle physics. The destination is worth the journey. The leading theoretical candidate for dark matter is a class of particle called a WIMP, a weakly interacting massive particle. WIMPs, if they exist, are not exotic in the way science fiction imagines. They carry mass. They respond to gravity. They drift through the galaxy in vast, diffuse clouds. What makes them invisible is simpler than it sounds. They do not interact with the electromagnetic force. Light passes through them. They pass through light. A WIMP could travel through a wall of lead, a light year thick, and emerge unchanged on the other side. But WIMPs are predicted to interact with one another under rare and specific conditions. When two WIMPs collide, not bounce, not scatter, but collide with sufficient proximity, they annihilate. Their combined mass converts entirely into energy, following the most famous equation in physics. That energy manifests as standard model particles, quarks, leptons, gauge bosons. These decay products cascade downward through successive interactions until they produce something detectable: gamma rays. The energy of those gamma rays is not random. It is determined by the mass of the original WIMP. A heavier particle produces higher energy photons. A lighter one produces lower. This relationship is precise, calculable, and, critically, predictable in advance. If a WIMP has a mass of 43 billion electron volts, the gamma ray spectrum produced by its annihilation through standard model decay channels will exhibit a characteristic cutoff and spectral feature in the range near 20 billion electron volts, depending on the dominant annihilation channel. That is exactly what Totani found in the Fermi data. The coincidence, if it is one, is striking. Supersymmetry, a theoretical framework extending the standard model of particle physics, predicted decades ago that WIMPs should have masses in the range of roughly 10 to 1000 GeV. The 43 GeV implied by Totani's signal sits comfortably within that window, not at the edge, not in an implausible corner, but in a region that multiple independent theoretical models identified as probable before this data existed. Let that settle for a moment. Energy alone, however, is not enough. A gamma ray excess at 20 GeV could originate from dozens of astrophysical processes: supernova remnants, active stellar nurseries, binary star systems with extreme magnetic fields. What distinguishes Totani's finding from a generic excess is not the energy, it is the shape. Dark matter, according to cosmological simulations developed throughout the 1990s and refined over 3 decades, does not distribute itself uniformly through a galaxy. It forms a halo, a roughly spherical cloud densest at the galactic center and thinning gradually toward the outer edges. Computer models of galaxy formation run on supercomputers simulating billions of years of gravitational evolution consistently produce this structure. The Milky Way is predicted to sit embedded within such a halo, like a disk of luminous matter suspended inside an invisible sphere roughly 10 times its visible diameter. Totani's spatial analysis of the Fermi data reveals that the 20 GeV excess is not scattered randomly across the sky. It concentrates around the galactic center. It extends outward in a distribution that thins with distance, and the rate at which it thins, the density profile, matches the Navarro-Frenk-White profile, a mathematical model of dark matter halos published in 1996. A signal predicted 30 years ago, in a shape predicted 30 years ago, at an energy consistent with particles predicted 40 years ago. By contrast, conventional astrophysical sources do not naturally produce this geometry. Pulsars cluster in the galactic plane, not in spherical halos. Cosmic ray interactions trace the distribution of interstellar gas, which is concentrated in spiral arms. Unresolved point sources would produce statistical noise, not a smooth, symmetric distribution centered on the galaxy's gravitational heart. This is what elevates the finding from interesting to significant. Yet the history of dark matter detection demands more than significance. It demands survival. survival through replication, independent analysis, and the systematic elimination of every alternative explanation. On this front, the record is unforgiving. In 1998, the Dharma-Nye experiment at Italy's Gran Sasso National Laboratory reported an annual modulation in its detector consistent with Earth moving through a galactic dark matter wind. Its successor instrument, Dharma-Libra, continued and extended that claim from 2003 onward. The signal persisted for over 2 decades. No independent experiment has ever reproduced it. The Xenon, Lux, and Panda X collaborations using different detector technologies in different locations found nothing where Dharma predicted a signal should appear. In 2013, the Cryogenic Dark Matter Search reported 3 candidate events in silicon detectors. Statistical analysis later showed the result was consistent with background contamination. The claim was quietly withdrawn. The Fermi Telescope itself generated one of the most prominent false leads. The so-called galactic center excess, identified around 2009, initially appeared consistent with WIMP annihilation. Subsequent analyses by multiple groups demonstrated that unresolved millisecond pulsars could account for the entire signal. What looked like dark matter was, in all likelihood, thousands of rapidly spinning neutron stars too faint to detect individually. Every previous claim collapsed. Each time, the explanation was mundane. What separates Totani's analysis is methodological resilience. Unlike earlier studies that relied on single energy bins or narrow angular regions, this excess appears across multiple energy channels clustered around 20 GeV. The halo morphology holds under different analysis cuts. The paper includes systematic uncertainty quantification, accounting for Fermi's instrumental response, atmospheric contamination in low energy bands, and modeling of known gamma-ray sources that were subtracted from the diffuse background. After each correction, the signal persists. It persists. That is not confirmation, but it is unusual. Still, there is a problem, one that Totani himself acknowledges. Several astrophysical sources can produce gamma rays at precisely 20 GeV, millisecond pulsars. Cosmic ray protons colliding with interstellar hydrogen through pion decay, unresolved point sources sitting just below Fermi's detection threshold, individually invisible but collectively bright. Any one of these could mimic the spatial and spectral signature of dark matter annihilation. Ruling them out requires not just reanalysis of existing data, but entirely new observations from instruments that do not yet have. The burden of proof does not rest with the signal, it rests with the claim. A gamma-ray excess at 20 GeV exists in 15 years of Fermi data. That much is established. Between observing an anomaly and declaring it dark matter lies the most demanding gauntlet in physics, the systematic elimination of every conventional explanation. Not most of them, every single one. This is where the analysis either survives or collapses. Professor Tomonori Totani, working alone at the University of Tokyo, chose to walk directly into it. Consider the galactic center. Within the innermost few hundred parsecs of the Milky Way, matter reaches extraordinary concentrations. Stellar remnants crowd together, neutron stars, white dwarfs, black holes in tight orbits around companions. Among them, millisecond pulsars spin hundreds of times per second. Their magnetic fields accelerate particles to relativistic speeds. Each one functions as a compact gamma-ray engine. Thousands of these pulsars are predicted to exist near the galactic center. Only a fraction have been individually detected. The rest sit below Fermi's angular resolution threshold, too faint to isolate, too numerous to ignore. Collectively, their combined emission could produce a diffuse glow of gamma rays centered on the galaxy's core. Could that glow mimic a dark matter halo? Totani's paper addresses this directly. Known pulsar catalogs were subtracted from the data. The remaining diffuse emission was modeled against predicted pulsar population distributions. The excess persisted. Its energy spectrum, peaking sharply at 20 GeV, differs from the broader spectral shape typical of millisecond pulsar populations, which tend to produce softer emission that drops off above a few GeV. The distinction is measurable, not overwhelming. Pulsar models can be adjusted. Assumptions about undetected populations can be revised upward. What cannot be easily adjusted is the morphology. Pulsars concentrate in the galactic disk and bulge following the distribution of old stellar populations. Dark matter halos extend spherically outward from the galactic center. Their density falls with distance according to specific mathematical profiles, the Navarro-Frenk-White profile being the most widely used. Totani's excess follows the halo geometry, not the disk geometry. That is a spatial argument, not merely a spectral one. It carries significant weight, but it does not carry certainty. A second alternative demands equal scrutiny. When high-energy cosmic ray protons collide with interstellar hydrogen nuclei, the interaction produces neutral pions. These decay almost instantly into pairs of gamma rays. This process, hadronic pion decay, generates gamma ray emission across a broad energy range, from roughly 1 GeV to well above 100 GeV. The 20 GeV window sits comfortably within it. The challenge is geometric. Cosmic rays propagate outward from their acceleration sites, supernova remnants primarily, and interact with whatever gas they encounter. The resulting gamma ray emission traces the distribution of both cosmic rays and interstellar gas, which concentrate heavily in the galactic plane. Producing a spherical halo-like excess through this mechanism would require an unusual cosmic ray distribution that coincidentally mirrors the predicted dark matter profile. Not impossible, but requiring a specific, fine-tuned coincidence to mimic the very signal being searched for is, at minimum, uncomfortable. There is a third consideration. It concerns not astrophysics, but methodology. The Fermi Large Area Telescope's effective collection area is not constant. It varies with photon energy, incidence angle, and the spacecraft's orbital position relative to Earth's gamma-ray bright atmosphere. Background contamination from cosmic ray particles, misclassified as gamma rays, introduces systematic noise that must be carefully modeled and subtracted. These instrumental effects are well characterized by the Fermi collaboration, a team of hundreds of researchers who have spent over 15 years calibrating the instrument. Totani's paper includes systematic uncertainty analysis. It accounts for effective area variations and background contamination models. The excess survives these corrections. Yet, in modern high-energy astrophysics, a discovery claim of this magnitude typically emerges from within the instrument collaboration itself. Access to proprietary calibration data and internal cross-checks provides layers of verification unavailable to external researchers. One scientist, however rigorous, working with publicly released data, faces an inherent asymmetry in verification depth. The Fermi collaboration has not issued a statement confirming the excess. Independent researchers have begun reanalyzing the same dataset using alternative background models and different spatial templates. Some preliminary efforts report a signal consistent with Totani's findings. Others suggest the statistical significance may be lower than reported. The halo morphology may be less cleanly separated from disk emission than the paper implies. This is not failure. This is the mechanism functioning precisely as designed. One hypothesis, subjected to independent replication, either strengthened or dissolved by competing analyses. The signal cannot yet be attributed to dark matter, nor can it be comfortably attributed to pulsars, cosmic rays, or instrumental artifacts. It occupies the most difficult position in science, unexplained but unconfirmed. What is needed now is not another reanalysis of the same 15-year dataset. What is needed is an entirely independent measurement from an instrument operating on fundamentally different principles. That instrument has just completed construction. Its primary mirror spans 8.4 meters. Its camera contains 3.2 billion pixels. And on the night its 10-year survey begins, the first photons it collects will carry information about. The signal sits at between 3 and 4 sigma, a statistical measure indicating that the probability of this excess arising from pure chance falls below roughly 1 in 1,000. In particle physics, that threshold is considered interesting. It is not considered discovery. Discovery requires 5 sigma, a 1 in 3.5 to million chance of a fluke. The gap between 3 sigma and 5 sigma is not a technicality. It is the distance between a promising anomaly and a confirmed detection, and in the history of dark matter research, no candidate signal has ever crossed it. This is where Professor Tomonori Totani's 20 GeV excess currently resides, strong enough to survive peer review, strong enough to warrant publication in the Journal of Cosmology and Astroparticle Physics, not strong enough by the standards of the field to constitute proof. The Vera C. Rubin Observatory sits on Cerro Pachon in northern Chile. Its 8.4 meter primary mirror feeds the largest digital camera ever constructed for astronomy, 3.2 billion pixels, each one sensitive enough to detect a candle flame from the distance of the moon. Over 10 years, this instrument will photograph the entire accessible sky every 3 nights. The catalogue will contain approximately 20 billion galaxies. Its relevance to dark matter is gravitational lensing. Mass warps space-time. Dark matter, whatever it is, has mass. When light from distant galaxies passes through a region of concentrated dark matter, that light bends. The distortion is subtle, a slight elongation of a galaxy's shape, detectable only when averaged across millions of sources. The pattern that emerges from those millions of measurements reveals the 3-dimensional distribution of invisible mass with extraordinary precision. Here is the test. Totani's gamma ray excess traces a halo-shaped distribution centered on the Milky Way's core. If dark matter annihilation is responsible, that halo must correspond to a real concentration of gravitational mass. Rubin's weak lensing survey will map that mass independently, without reference to gamma rays, without dependence on WIMP theory, without reliance on a single author's analysis. Should the gravitational map align with the gamma ray halo's geometry, the case for dark matter annihilation strengthens dramatically. Should it diverge, the signal must originate elsewhere. Early survey data capable of testing this alignment is expected within 2 to 3 years of full operations. The central question posed at the beginning of this investigation was direct. Is the 20 GeV gamma ray excess found by Totani in the Fermi dataset the first observational evidence of dark matter particles annihilating, or is it another false signal in a search that has produced nothing but false signals for 92 years? The answer, supported by the evidence assembled across this analysis, is that the signal represents the strongest candidate for dark matter annihilation ever recorded in gamma ray astronomy, but it has not yet reached the observational threshold required to constitute detection. It is a testable hypothesis, not a conclusion. The distinction matters enormously. What this case reveals extends beyond one anomaly in one dataset. The search for dark matter has entered a phase where instruments built for different purposes, a gamma ray telescope, a visible light survey, underground particle detectors, can now cross-check one another's results. For the first time in the 92 years since Fritz Zwicky inferred invisible mass from the velocities of galaxies in the Coma cluster, the question of what dark matter is has become falsifiable on a timeline measured in years rather than decades. A single researcher at the University of Tokyo identified an anomaly. The global apparatus of observational astronomy is now positioned to determine whether that anomaly marks the boundary between the known and the unknown, or simply another refinement of what we already understand. The Fermi telescope continues to collect photons. The Vera Rubin Observatory has begun its survey. Somewhere between those two instruments, 85% of the universe's mass is either revealing itself or remaining, as it has for nearly a century, silent.